So today we're just going to be reviewing for our exam next week on Tuesday. So it's going to be a lot of examples today. First off, so I will be recording this. You can come back and watch it. First, I want to talk about how you can take the exam. The easiest way is just show up. You can bring a laptop, bring a book, bring notes. I strongly recommend making a note sheet because it will speed things up for you. It also really helps to study. It's easier to look through the note sheet than it is to look through the whole book. The other way is you can take it remotely online. The way this works is I will post at the start time of class, I will post a PDF file and an assignment on Canvas. You can then download that and print it out if you'd like, or just download it and use it on a tablet. And then at the end, you're going to need to convert it into a PDF. That may involve taking pictures of it and converting it, and then uploading it and submitting it on Canvas on time. Those are the two ways you can do it. In class is easier and students tend to do better, but if you're unhealthy, unwell, whatever it is, you can take it remotely. And the differences are a couple of percentage points on average, so it's not too much worse to do it online. Make sure when you take the exam to read the instructions thoroughly, because oftentimes I will give hints to the problems in the way I ask the question, and you also don't want to screw it up and answer it the wrong way. So I may say something like, using Boolean manipulation, provide for me the minimum sum of products expression. And if you go and bust out a K-map, you can get to the right answer, but you won't have answered the question. So make sure you read what the question says. Don't just kind of skip to what you think the answer should be. As for what goes on the exam, it will cover anything from the homeworks, the lectures, or the labs that we've done. Any of those are fair game. I won't introduce really like new devices, new gates, but you'll see new configurations of those things. So like we've dealt with NMOS and PMOS devices making AND and NAND and NOR, right? But I could come up with another gate, a string configuration, and we'll go over a simple example of that and ask you, what is the function of this circuit, right? So be aware, it has a potential for a lot of different content that might be on it, but I will cover some of the things today in questions that will almost certainly be on it in some form. Okay. With that, I'm going to just go ahead and jump into the content that I kind of expect you guys to know, and then we'll do some examples. So first off, starting on page 31 in the book, you have a list of theorems, Boolean algebra theorems. Any of those are fair game, but two of the most important theorems that come up all of the time is theorem 16a and theorem, De Morgan's. So 16a is the one that just says if you have x or not x and y is equal to x or y, right? And the reason for this is pretty simple. If you just look at the truth table, so if we have x, it's true. So these two are true. And then not x and y is this, right? Well, I wrote them as a and b, but I can write them as x, y. So this is not x and y is a 1. And if you just look at that truth table, hopefully you can recognize that as an OR gate, right? And so that's x or y. Okay. And then De Morgan's, we'll probably do a couple of these examples coming up, but De Morgan's says something like, if we have A and B or not B and C. And I ask you to give me an expression for the complement of F. This is one way that I could ask a De Morgan's question. Give me an expression for the complement of F. Well, that's what De Morgan's does, is it gives us the complement. So we would say that F bar is equal to not AB or B bar C. And then we, in order to implement De Morgan's, right, we take whatever's in the bar, look at the terms, we take the complement of the terms and then flip the gate. So ands to ors, ors to ands. But the trick is we're not worried about these AND gates necessarily yet, right? Because what we're looking for is when I say the terms, it's this and that. So it's equal to not and B or not, sorry, and not B and C. And then we just apply De Morgan's again, each of those separately. So that is equal to A or B, because this and becomes an or. And then we complement the terms, they're not complemented, so individually it's A, not B. And then same thing here, we complement, we have a not B, so not B is just B or not C. Now, something that I want you guys to get a feel for is the way modern circuits work is inverters are cheap. And for some technologies, they're literally free. And when I say free, what I mean is the way the circuits are built produce both the complemented and non-complemented versions of an output. This is a really common thing that you'll see in computer architectures. So if you're asked the question, something like, let's say we have a truth table. I gotta turn the camera a little bit. And I'm not going to write all the 0, 0, 1s, whatever, but, and this may be a trivial circuit, I don't really know. Okay, let's say I have this, and I ask you to give me a minimum sum of products expression for this. That's fine, this is pretty easy. There's two ways that you can kind of do that. And obviously we're going to use K-maps if we have the choice. If we don't, and I ask you to reduce that, then the two valid ways are to, one, you'd start by saying F is equal to, well, the sum of the min terms, right, of everything that isn't 0 or, well, 0, 1, 2, 3, 4. So it's everything that isn't 0 or 4, right? So 1, 2, 3, 5, 6, 7. And I would write those out, and the min terms are something like not, or, and so on, right? But an equivalent way of writing this is using the product of sums expression, where F is equal to the sum of max terms, just 0 and 4. Now, if I do this, right, so when we write the product of sums expression, we complement them if it's not 0. So min term 0 is A or B or C. And then for this one, it's not A, right? Because it's a 1 or B or C. Okay, so now that is a product of sums expression, but I asked for a sum of products. But inverters are free, so let's just write F bar is equal to sorry, I just did De Morgan's in one go. I think I did it right.
Yeah, it looks right.
Right. And because I don't really care about the inversion, right? At the end of the gate, it's just like this and then inverter. Done. So that's a totally fine way to handle that if it happens to be easier. This may or may not be right. This isn't even the simplest form though yet, right? Does everyone see? Because I have a B bar C, B bar C. So I really have A bar or A. Right? So sometimes flipping that is really simple. And you can sometimes do the same thing for the other reason. So you'll invert it in order to simplify, and then I can reuse De Morgan's to find F and end up with a product of sums, right? Because again, F is just equal to make sense? Okay, and you can always fill out the truth tables to make sure that that is correct. I will probably ask you some questions about truth tables, but we've done them a whole bunch, so I have confidence that you can handle those. Redundancy. This is an idea that keeps coming up, right, all the time. So redundancy is an example that I want to do. And I have posted the solutions to homework 2 and the first half of homework 3. So I haven't yet got to chapter 3. I'll work on that today. And you'll see the solutions for the rest of the homework to roll out throughout this week and weekend. I'll get that out to you since study. This one was on the homework, and it just was asking for, and I'll make the caveat, in the solutions, you're gonna see the more recent ones, I started using ABC. Because it's easier to read than X0, X1, X2. So A is X0, B is X1, and so on. It's pretty easy conversion, but I think it's easier to read, especially because I don't have the best handwriting. And so A, B, and C is easier to tell. So this one, do the one I wanted to do? Let me double check. Oh, shoot, I want to do 23. Okay. And then I could ask you 2 different ways the same question. I could ask you to find me the minimum product of sums expression for this circuit. And then I could ask it of either using K-maps or without using K-maps, right? And then I will say something like, show your work. And if all that happens is you show up with the answer, you get no points. Because I want to know that you did it, not that a computer did it. okay? So what you do in these types of questions, when you have this type of simplification, is you want to look for any two terms that have variables that differ by only one, right? We call that logic adjacency. It's the same principle that we use when we're using K-maps. So in this case, term 1 and 2 differ only by C bar, and terms 3 and 4 differ only by B and B bar. That's one variable that's different. They're logically adjacent. That means if we multiply them through, we're going to end up with lots of simplification. So I've done one of these examples before, and I'm going to show you kind of the easy way to do this if you are wanting to. So my first multiplication is A and A, which I can just write as A, right? I can make that simplification in my head. I expect that you guys can too. It's fine. And then what I can do is, now that I know that anything with A and something is redundant, right? So that's the term, redundancy. So the rest of these don't matter. A and B, A and C bar don't matter. Now next, I can see that next time I'm going to have B and B, which is just B. And now because of redundancy, I know I don't need to take care of any other B and terms. So this is just going to be B and A and B and C bar. I no longer care. So lastly, I have the C. But C, because of the logic adjacency, is going to be A and C, don't care. B and C, don't care. And then C and C bar, which is 0. I don't care. Done. One step. Now eventually, so like when I was writing the homeworks, I had to prevent myself from just skipping to that. Because what I know it's really saying is I just get to keep the common terms, right? The things that don't change, and discard those that do. That's what the K-map's doing. That's what the adjacency is doing here. It's the same thing. Keep what's the same, toss what's different. Okay. I don't know how fast this is going to go, this review, so I may circle back around to number 44 from chapter 2. If I don't, take a note. 44 is a good one to review because I like it as far as an example of redundancy. But I may circle back around to 44.
Which homework?
Sorry, chapter 2, number 44. I don't know if that was homework 2 or 3, but I know it's a good question. You know what? Actually, maybe I will do that one because of that vocalization, because it is a tricky one. And if I do something like this on an exam, I want you to recognize it really quick. So this says, let's go ahead and simplify the following expression. Okay. So the issue we have is you could spend a while looking at this and go, but there's no way to simplify. There's no terms in here that I could simplify. Now, I could again ask this two ways. I could ask, using Boolean manipulation, simplify this function. Or I could ask, just simply simplify this function. Those are both valid ways. The difference being, if I just asked you to simplify without any qualifiers, you could turn this into a K-map. And I want to show you how you do that. So I have A, B, and C. And then I have, actually, do you know what? I'm going to skip the truth table. Let's pretend you're on an exam. I don't think I've done this yet. Let's pretend you're on an exam and you don't have time to write out the whole truth table because you're worried about the time crunch. Okay? A, B, C. Okay, so now all I have to do here is go, when is this true? Well, if I have A and not C, it's true. Okay, so A and not C. Both of those are true. Now I have A and B are true. Well, that's A and B are true, regardless of what C is doing, so it's that whole column. Next is not A, not B, that column. And lastly is not B and C. Okay, not B are these two columns, and C is that column. And then I just do the K-map, right? The K-map is going to be those two circles. Okay, well, this is actually handy because if you weren't sure on this question, and even if I asked it the other way, this is an easy simplification, right? I just say, well, F is equal to what doesn't change? Well, A doesn't change, B changes, C changes. So that first one is just A. And now we know on the second one, C changes. So the only thing that doesn't is B bar. I know what the answer is now. I know where I'm trying to get to. What that means is I know that the C is somehow just going to come out of this whole thing. That's a clue. This is a verification. It took me almost no time, right? And I don't need to take the time to fill out the truth table because I can just fill in the K-map that way. All right, so let's go ahead, keeping in mind that it's A or B bar. And how do we simplify this? Well, what you really want to start doing is looking for terms that if you add something to it, right, we're using redundancy in reverse, then I'm going to get simplifications. So sometimes you just have to guess, which is frustrating, but something that I'm going to do for myself is I'm just going to go left to right and start looking. Like I have A and C bar and A and B. Well, I can easily get a C and C bar on this term by spreading this out and calling this A, B, C or A, B, C bar. Right? And that's just multiplying this AB by C or C bar. I can multiply by 1, right? And it doesn't change. That's all I've done here. I've just skipped explicitly drawing that out. And now I can do things like, well, I have an A and C bar here and an A and C bar here. So I'm going to have sorry, what did I do wrong? ABC bar. Oh, and then I factored out the C bar of this term and that term of AB on here or A. Why is that useful? Well, redundancy. It's redundant, right? If I have A and A and B, the A is always true. So the A and B is true. So that term can just go away and give me back my A and C bar. And then I have this nice convenient ABC left. It didn't really add any complexity to my circuit, but it's going to be convenient later for simplification. So I end up with A, B, C, or let's not forget what we still have. So this split out to that, so it's covered. And I do want to point out actually something right here. So this is, I'm going to do how I did it in my answer, just so I don't get too lost and astray while doing this. This step is actually unnecessary. I didn't need to do this one. When I later went back and looked at this, I was like, oh, that first step was, I didn't need it. But I wanted to do it to show you that making that mistake isn't really an issue. It's fine. Because it'll come back around as long as you continually make good guesses. This was still a good guess. It just wasn't the perfect guess. Then the next one, I'm just going to move on and do my A bar, B bar, and be like, okay, well, if I add an A here, then I have an adjacent term, right? So I'm going to split this guy out the same way using C and C bar. Right, and then I can factor out the B bar C. Is that what I did? I'm going to do a caveat. This is hard. If I do one of these on this test, I'm going to allow a substantial amount of time for this because they're tricky, as you can see. I've already done this one, and I'm like, what if I do? So the only thing I have is I have this B bar C term that is in common with that one, but it doesn't yet match. So splitting this one out can actually help as well in order to get the A's. Because here I've added the C, here I've added the B. I could also just factor out the C and say C, A bar, B bar, B bar, and simplify it down that way, right? I could do the same thing. And I'm going to figure out which one of those two that I did. So I have AC bar, ABC. Then this one could be C or C bar with the BC. Or A bar B. So this is the one that I chose to do. So I did the A bars. Which then that cancels and goes away. So I've handled these two terms. And then I have to start dealing something with this guy, right, the B bar C. And that one is also, I can do the A or A bar multiplication in order to get it out. And I can end up with A C bar or a C times B or B bar, taking this one. I got lost. AC, ABC. I'm going to keep that one for now. A bar B, or B bar, or BC. Okay. And now I'm starting to do some things. So this is why I said this one wasn't all bad, because I had this guy hanging out for a long time, but now I have a like term, which is kind of convenient. I like that. I like the BC there. So that's something I can start looking at grouping. And I can go so far as to say, what is true about that B and C and the A and B and C? The A and B and C is redundant. I don't need it anymore. Well, so it goes away because it's redundant with that. And now I've got another term that's equal to that one, right? Another expression, they're equal. But this one has one fewer terms. I've made progress, that's good. And now I can just start kind of repeating that same kind of educated guess, right? It's not always, you're not always going to get the best one on the first try. But what you're going to start doing at the same time is, what can I add to these things in order to build towards simplification? Yeah. What do I need to add to, say, a BC to get that? Well, What's interesting here is when I look at it and I go, oh shoot, BC and AC bar are kind of far away from each other. But if I kept that ABC, then the ABC and the AC bar are still close, right? It's I could get an ABC bar and then they'd be similar, and I could simplify from that. So I probably would want to keep that one or just carry it down, right? And I can see that as I've made this move and go, what am I adding? Well, we'll just use something redundant. And you can kind of do that with a couple of easier ways too. I haven't tried this simplification method, but I can just say something like, well, A and C bar and A and B bar. So really, if I have AC bar or A B C bar, I can just add that one in because B bar, C bar. I can just add that because it's redundant with this guy. If this is true, that's also true. I don't necessarily have to do that multiplication and get two terms if I don't need it, as long as I hold to redundancy. Okay, I'll try and include one of these. I'm going to send out some practice homeworks, some practice problems that you can optionally go through, and I will include something like this. And if you see something like this, I will try and remember to include in the instruction that says something like, hint, you're going to have to add terms in order to simplify it. And I will probably also start with only 3 terms rather than the 4, just so it's a little easier to simplify just for the exam. So be aware, find some, practice them. The digital logic solvers that some people want to use as a crutch don't do very well with these ones at all. They might give you the answer, but you can find the answer in like 2 seconds with a K-map anyways. So be aware, something like that might show up, and it's likely to be one of the hardest problems. The other one is, if you struggle with them as much as I struggle with them, do it last, right? Just general test taking tip. I curve. So if you all do terrible, I'll just curve the average and everyone will do better. In general, in this class, I don't have to curve. I don't know if I've ever curved more than 1 point in this for the 2700. It's just, my exams aren't that terrible as long as you've prepared. So, but what you do want to keep in mind is you're kind of chasing points, right? Like, as long as you add up to a good enough number, you're fine. So if you see something like, I have no idea how to do this, don't spend your first half hour trying to solve it. Go get the ones that are easy. Go get all the points that you can, and then come back to those that were hard, right? That's true for most of your classes. Go get the points you know how to get, come back to the ones that are harder. Okay. Man, sometimes this class goes by so fast. Universal gates. If I want to make a NAND gate circuit, if I ask you, please make me a minimum circuit using NAND gates. Well, NANDs are easy to make out of this structure, right? If we follow that bubble pushing method. What that means is I need a sum of products for NAND, right? So if NAND, sum of products, which means use the ones, right? Either min terms or circle the ones in your K-map, whatever you need to, whatever method you're using. Similarly, if you need NOR, do a product of sums, which means use the zeros. If you wanted to go back and look at one homework of that, there's a chapter 2's number 39 is what I have written down. I think that might have been out of homework 3. Yeah, I don't worry. I wrote it down. I trust myself for writing it down. I think that note isn't going, yes.
Just to clarify on the zeros for the K maps, the implicants are now zeros, not the ones, correct?
Correct.
Okay.
And we'll do one of those.
Okay.
Assuming I don't randomly run out of time. We're doing okay. We're about halfway. But this is the most important one. When I ask you that question, keep this in mind because that's how you'll end up with the right answer easily. It's not impossible to go the other way, right? Because you could also just take the ones and then do De Morgan's theorem on it and just throw an inverter at the output. And I would end up with the same result, right? So if in this circuit, if I use this circuit as an example, and I told you to give me the minimum NOR gate, it's pretty easy, right? Because the zeros are very few. If I told you to give me a minimum expression using a NAND gate, your first instinct would be to be like, all right, let's do all the ones and do a whole bunch of algebra. It's equivalently easy to just use the zeros, perform De Morgan's, and then throw an inverter at the output so you end up with F, right? So the output gate in the case of a NOR gate, which is equivalent to writing this one, right? And then, so I have this, and here, if I had gotten this using De Morgan's, would be F bar. So then I just throw an inverter, and that's now F. Now, I don't require that you draw your inverters as NAND or NOR gates in your homeworks. I may ask you to do that for the exam. So be prepared to think about what does a NAND or NOR gate look like? What is the wiring configuration in order to make it function like an inverter? There's a couple different ways to do it in both, but I'm going to leave that hanging there for you guys to solve on the exam with warning. Okay. You can use it in truth table pretty easily. The truth table is like your hint for that. Okay. I will also ask you gate level questions. So when I say, transistor level questions and gate level questions, we'll do both. Remembering that we have PMOS, we have NMOS, and I could simply ask you, I could draw one of these and say, what is this device called? Yeah, exactly. So that's like the easiest one, the bare minimum that I would want you to know. I could even simplify it more and literally just draw one of these, ask you, what is that? Right? What type of device is that? Right? NMOS. PMOS has the bulb. I could also take this further and start mixing some ideas. And I could ask you, what is F? I mean expression for F. Still daunting? Or do you feel okay? What would you do? Yes, make a truth table. And it's not a hard truth table, is it? I literally have EN and D. EN usually means enable, and F. Okay? So what happens if I have 0 and 0? Well, I'm just going to trace this through. So I'm going to say this is 0, enable 0. If I have 0 on enable, that means I have a 1 here, right? What is the output of my NOR gate? If I have a 1 and a 0 at the input. Zero. Again, if you're not sure, truth tables, shoot, I'm off the map. Are your friend. We know that an OR is 0, 1, 1, 1, which means a NOR is just not that, right? The only time where I'm a 1 in a NOR gate is if they're both 0. They're not both 0, therefore I have a 0. What does the NMOS do when it sees a 0 at its gate? It's open, absolutely. Okay, so if it's open, that means if this is closed, it draws up. So let's find out if that is closed. Well, I have a 0. This is kind of a weird way to draw it. Let me put a 0 here and a 0 there. What do I get with a NAND gate at this output if it's 0 and 0? 1. What does the PMOS do if it sees a 1? It opens. So what is F? Because we're not connected to ground and we're not connected to VCC.
There's no power.
Is not driven. So the way that you'll see this appear in Vivado, so I would accept X because we've really talked about that. Another, even if at this point, if I hadn't gone over this question and you put a huh, I would be totally okay with that as well. The way you'd see this in Vivado simulation, Z. It's not driven. It's what we call high impedance. It's just there. We do this kind of thing all the time on purpose because for nodes that function as inputs and outputs. So if you want one pin to be an input or an output, then what you do is either you have it, if it's currently function as an output, then you drive it, you turn on the enable. If it's not driving the signal, then you turn off the enable, and then it can accept an input because it's not driving. Real world application for that. This is how you would solve that. Now let's go ahead and do 0, 1. Okay, well now we have 1, 1, that's still a 0, right? And now I have 0, 1. So it's 1 here, 1 and 0. What do we get? A 1, nothing changes. Well, that's starting to make sense, right? So if it's not enabled, it's not anything. If it is enabled, now we should expect something to happen. So let's switch. I'm just going to erase these ones that I have to keep it clear. To putting enable at 1 and D, data, is what we would call that one, at 0. Okay, well, if we have a 1 here, we get a 0 here. What is 0, 0 for that? 1. What does an NMOS do when it closes, which means connected to ground, which means 0. Now we need to make sure that we don't have a also to VCC. So this is a question I could do, and I could present one and say, is there a scenario in this circuit which is invalid or would damage the circuit? Or, I could ask it a number of ways, but the general idea is there a case where I'm connected both VCC and ground, in which case I'm just dumping an infinite amount of current across them and I blow up the devices. This case, let's make sure that doesn't happen, right? Well, if I have a 1 here, what do I have here? So I have a 0 here still, because the D is still 0, 1 here. What happens if I have a 0, 1 at the NAND? Which means the PMOS is doing what? Open. Perfect. Great. 0. And I mean, this is a 1. You can prove it if you want, but there we go. So what is this device then? How could you just, I may ask you, what is another way to describe this device? It's a buffer with an enable. Right? Because if the enable is on, F is just D. It's a buffer with an enable. So expect something like this, where either I'm going to give you a circuit that is entirely transistors and ask you to draw me the function, which this is just the first step, right? The truth table is just the first step. Then we can turn this into a function. So expect that I will either give you a circuit that is all transistors and ask you to write me a function, or give you a mixed circuit that is gates and transistors and ask you to give me a function. Expect one of those on the exam. I love these questions. They're lots of fun. They're borderline impossible to cheat on, so they're great questions. Okay, K-maps. Main takeaway from K-maps, I may do a 6 variable K-map, but I doubt it. The only reason I would ask you to do a 6 variable K-map is if it's in conjunction with a 4 input mux. So we've talked about muxes. Muxes are important. When we do a 2 input mux, we have 1 select, where select, if select is 0, we go with that pin. If select is 1, we do that pin. For a 4 input mux, we have S0 and S1. And if you pick 0, 0, 0, 1, 1, 0, 1, 1, it attaches that output. This is the only circuit that I can think that I would ask you to do a 6 input K-map. Because, right, this is A, B, C, D with select 0 and 1. Other than that, I won't ask you, and it's only because the muxes are so important in digital design. Okay. Other than that, I will probably send you an email letting you know by this weekend if I've decided to do that one or not. Because I need to do it. I have to do it and see how hard of a question it actually is before I inflict that on you guys. And if I do a 6 variable K-map, I won't do one of that other question where you have to make it more complicated before simplifying it. So I did both of those. That's probably the whole exam, let's be honest. Okay, K-maps. Again, just kind of repeating what I said before. If I have a K-map, and I have a truth table, keep in mind, if I write the truth table this way, then always the first one is the first row, and the second one is 0, 0, 0, 1. So if you're trying to fill in the K-map quickly from a truth table, I'll just do the first 8, right? So I could just, as long as I know the order that this is, I can just start copying really quick. 0, 1, 1, 1, 0, 1, 1, 1, then 0, 1, 0, 1, 0, 1, 0, 1. Right? We can do that quickly. Remembering, don't make the mistake that I did when I was showing this before. This is your third column. So then if we do on 1101 here, then I would do 1101. And then let's just say the rest of these are 0010 or something. Okay. K-maps. Remembering that we have 2 different ideas that are really important. We have essential prime implicants and selective prime implicants, right? Find the big implicants is the great way to start on this one, no matter what you're doing. This one, the biggest ones I see are 4s. Does anyone want me to go through this K-map, or should I spend my time elsewhere? Okay. Remembering the most important one, if you end up doing a product of sums, you take that which doesn't change, so A and B, and take the complement. So it's A or B bar, and then you have C doesn't change or C, right? Product of sums. People mess that up. Read the instructions. Make sure you see which of the 2 types I'm asking for. When you're doing the conversion to universal gates, remember the rule that I said with the NAND and NOR, which one you're choosing, because that will be on the exam probably. Let's do the next one that will be on the exam, which I like to just call design examples or a design problem, where I will simply ask you a word question and make you to turn it into a circuit. So it's going to say something like, let me think, I didn't write an example down. Well, we could go back to the light switch question, right? When I introduced it, is design me a circuit for a living room that has 3 lights. I want the light to toggle anytime one of the switches is thrown. Assume that all switches start in the off or down position. Does anyone think they could not do that? Does anyone want me to start walking through that? Because that's the type of design question. The other one that I did recently, right, was the 7-segment display. I could just ask, design me a minimum sum of product circuit to control LED number 5. Right? And then I would add something like, assume that 1111 is an error code, right? That would be a valid question. Those are the design examples. Next topic that you will have likely some questions on is just rudimentary VHDL, kind of like what you guys saw in the homework, where it will just ask something like, write the VHDL expression to achieve X. And it could be part of another question. It could be the LED and say, part 1 is design me the circuit that implements the minimum sum of products for LED number 5 in the 7-segment display. And then part 2, part B, would ask, write a VHDL expression to represent that circuit. I will try and specify, like, you don't need to write the architecture or the port or whatever. Or I may ask you, please give me a VHDL module, including the port and architecture declarations, that implements this function. Faculty fair game can ask, write me a VHDL module, including the ports and architecture that implements a full adder. Right? Because we've dealt with full adders, we built that circuit in lab, we talked about it in class. So that question by itself, I would expect that you know what a full adder is, or can look it up in the book, and then write the VHDL expression for it, including the port map, etc. Make sense? I won't ask you yet to tie multiple modules together. I don't expect you to be able to do the component declarations instantiations yet. That's next lab, so that will be on the next exam. So if I tell you you don't need the architecture declarations and you just wanted to write, the answer would just simply be that. Oh, semicolon, right? So you'd miss like a little bit for if you forgot that equal sign, you miss a little bit if you did that. You'd get most of the points as long as, even if you wrote this. If that's all you did, you'd still get a fair chunk of the points, but you would miss some. If you did this, you'd miss a lot of points. Because typing that in Vivado, I'm not quite sure how to pull that one off. It's difficult enough in Word to put those things over the top. Okay, there may be like some really simple true or false questions that would be like, or like multiple choice, like, well, I won't do it as multiple choice, I'll ask it simply, but I would ask something like, what is the difference between those two equal signs, right? This one is an assignment statement, that one is a comparison. Right, this is asking, is A equal to B? A lot of other programming languages use the equal, right? VHDL doesn't. It may be true or false. VHDL is case sensitive, the question that I could ask. VHDL questions will be pretty simple. They'll be stuff that you've done in homeworks or in labs. Actually, I don't know if we've done anything in labs yet. But it might tie back into what we have built in labs. Like I might ask about the comparator that we built in lab, right? That's a good question. I like comparators, they're fun. The last topic, we didn't get enough practice with these, so it won't be too hard of a question. But I could ask a question about timing diagrams or timing waveforms, right? Where I'm going to say one option of it is let's give you a circuit. And I don't know, this might be a trivial circuit that simplifies to nothing. That happens a lot when you hand draw them. And I could then ask you to draw me a timing diagram that shows all possible outputs for F. Now I will try and remember, if I do that question, to give you timing diagrams with at least as many lines as you need. I may give you too many. I do that a lot, actually. So you have something for A, B, C, and I would, a couple ways that I could do this is I could either have you do this, or I might provide A, B, and C, and I might just say, finish the timing diagram. It depends how much time I decide to make you spend on this question, right? So if you have to make your own, what you would do is just count in binary using A, B, and C. So take some divisions, and you would do, well, let's say A is our most significant bit, MSB. Any of the things I took a time out during class to ask to emphasize the vocabulary word, MSB, implicant, LSB, min term, max term, any of those ones that I emphasize in vocabulary could easily be a question that's either true, false, or short answer, or match the terms. But for these, if this is my MSB, then it's going to be 0, 0, 0, 0, 1, 1, 1, 1, right? And then B is 0, 0, 1, 1, 0, 0, and this guy just changes every time. Right? If I count with A, B, and C, then I cover all possible terms. And then then I would give you a couple of blank lines. You would use these for, I don't know, let's call it alpha and beta. Right? You can call it whatever you want. You can call it X and Y. And then you would draw what happens on alpha and beta as these all change. So in the case of alpha, right, if A and B are both 0, well, alpha is 0. Right, because it's just an AND gate. And then here, if B is 0, we get a 1 here. So beta starts at a 1. Well, then we step to the next time window and we still have A and B. So A is 0, B is 0. So alpha still is 0. And C has changed, and we don't actually care, right? Because if this is already a 1, this is an OR gate, so it's going to stay high. So then I can start seeing patterns, right? Like I know alpha isn't going to change until I have A and B. So A and B doesn't happen until way off here. So alpha is going to be low until that point, right? This is a likely question of some form. It may have A, B, and C and ask you to fill in alpha, beta, and F, or it could be 6 blank lines or 8 blank lines, just to trick you, because you may or may not want to assign X, right? You may want to draw A, B, X, alpha, and beta. And sometimes they'll give you like 9 lines, and you'll be like, why is there 9? What am I missing? It's just a trick. Notice I didn't do the X here because I don't need it. If you guys do, if you want to be thorough, don't be afraid of assigning it. This kind of question almost certainly happened. And then I could go further and ask you, part 2, please draw this circuit using universal gates. What do we do? Oh, pushing, right? And there's nothing tricky, because if I say just universal gates, I mean NANDs or NORs. If I'm not specifying, you can use both. So, boom, that's a NAND. That's a NAND. That's a NOR, I'm done. Right? I want it to be that easy for you. As long as you recognize bubble pushing, you're going to have an easy time. That leaves us with 7 minutes if anybody has any other questions of things that they're worried about. Now you're all experts, that's what I like to hear.
So if you ask something that we did in class, like the light switch or the full ladder that we've already kind of done the equation for, could we just say like, okay, we've done the equation in class, here's the equation?
Yes, yeah. I would expect you to write from class notes, write the equation. Yeah.
When's the exam gonna be available?
It'll pop up at the beginning of class hour, so it'll pop up at 8:59 probably. And then it will run until 10:20. I'll run it 5 minutes over for both the people that are online to have a few extra minutes to submit it online, and the people in class. Sometimes they'll linger and let us do some last minute things. I try not to be too time crunchy with it, but there's always a little bit of that. So 8:59 on Tuesday.
Okay.
It'll pop up on Canvas.
So this is next Tuesday. And then we don't have a lab on Monday, right?
Oh, yeah, it's a holiday. Yeah, so we'll skip over lab I think his title, well, no, it's not, actually, I fixed it. So we'll do lab 6, not next week, but the week after. And that one's just all VHDL, I think. Yeah. Okay, if that's all, I'll let you guys duck out early and go stress about the test for the rest of the weekend.
I do have some questions.
Okay.
I'll let you finish the recording and then.
Yeah.
No,